Hey everybody, and welcome back to the next part in our video series on building a chess engine in Python using Pygame. And so in this video, I'm going to go through the rest of the move solutions. So where we left off was the white pawn moves, and we did that together. And then I gave you the task of trying to write the rest of the moves on your own. And so I just want to go through my solutions. Now, if your solutions work, then that's fine. And so you don't feel like you need to have everything exactly the way that I did it. But I do feel like the way that I wrote these solutions is pretty efficient, and so I think it's a pretty good way of doing it. So um, and there's certainly many ways of doing it, and there's probably a few things that I've done inefficiently. So maybe there's some things that could be improved upon. But I'm just gonna start with the pawn moves and go from there. So hopefully, again, I'm not gonna type all these out. I'm just gonna show them and walk through them. So I left you with this idea of the black pawn moves, and hopefully you saw that it was pretty similar. There's white to move and then there's black to move. The main difference we have here is this: instead of the r-1 here for the board, we want to look at r+1. And that's basically it. Instead of white pawns which move up the board, black pawns move down the board. So we want to add to the rows here. So that's all this is. We're checking if r+1 is an empty square, then that r+1 is a valid move. And then if now the main difference here is if row equals 1, not row equals 6 anymore. Row 6 is where the white pawns start. Row 1 is where the black pawns start. Just recall that, if we're looking at our board here, 0, 1, 2, 3, 4, 5, 6, 7, right? So white pawns are on row 6, black pawns are on row 1. So if a black pawn is on row 1, we get to move it 2 squares, which we see here, row +2. So that's pretty similar. We're just doing +1 and we're making sure we start at row equals 1. Now captures is also very similar. We have to make sure that the column that we're writing is still on the board. So if c-1 is greater than or equal to 0, or c+1 is less than or equal to 7, we want to make sure it's between these values of 0 and 7. Again, just pointing out the fact that, like, if I have a pawn here on the edge, I don't want to check a capture off the board here, because that would actually be an index out of bounds. Now Python, when you do negative indexes, it actually wraps around here. So if I don't put that, I would actually be able to capture a pawn here or a piece here with my pawn over in column 0, and that would be a little bit weird, and we definitely would not want that. The reason I'm not the reason I'm not checking to see if r-1 or r+1 is ever out of bounds is because if a pawn makes it to the last row, it should be promoted to another piece. Pawns actually can't exist on those files. And so we never have to worry about a pawn moving off the board, because if it gets to the end of the file or to the end of that rank, either row 0 or row 7, it should be promoted to another piece. So that's why I'm not checking r+1 if you were wondering that. But a good rule of thumb to follow when you're programming with lists is that anytime you have a list you're checking the indexes of here or here, you should make sure that you are having some statement that's actually making sure that that stays in bounds. So even better than probably putting 7 here would actually be doing like length of self board just 0, making sure that it's within the bounds. But we know our chessboard's going to be eight columns, so we don't necessarily need to worry about that. But that's probably a little bit better practice, is using the length of the array in general. All right, so enough said on that. Hopefully that point was driven home for you guys. And we will have to add pawn promotions later. So I'm just gonna make a note of this. Let's add pawn promotions later. So right now we're not currently worried about that, but we should eventually add those in. The only other thing we have to make sure we change, besides just the pluses, the minuses to pluses, and this row 6 to row 1 here, is the fact that here we got to be capturing a white piece. If we're a black pawn, we have to capture a white piece. If we're a white pawn, we have to capture a black piece. And so make sure you change that as well. Other than that, it's pretty much the same. Okay, so let's move on. Rook moves. So the rook moves are a little bit complicated, but I want to show you a way of doing this that actually makes the code really succinct and really nice, and I'm going to talk through what's happening. So just to remind you guys of how a rook moves, a rook can move in as many spaces as it can in a given direction, while capturing a piece. It cannot jump a piece, so you'll notice that I cannot actually move to any of these 3 squares. I can capture the piece, or I could move to somewhere in front of it. I cannot jump my own pieces. So rooks can move as many squares as possible in that direction. So if you think about it, at any point in time, a rook could potentially move 7 squares in a direction for a completely open file. So for example, this rook here can actually move 7 potentially squares. 1, 2, 3, 4, 5, 6, 7. So we only need to check 7 squares, up to 7 squares in 4 directions. So you think of it like that. That's our pattern. And so the first thing I do is I define what these directions are going to be, the pairs of coordinates. And I'm using the first variable to represent how I'm changing the row, and the second variable to represent how I'm changing the column. And I'm going to use this pattern in all of the moves here. So I've got a list of tuples. So this would be the direction that's moving the row -1 and the column by 0. And so what would that be? That would be the direction up. This would move the row by 0 and the column by -1. So this would be left. So if I'm looking at these in just directions, this is up, left, right, down, and then right. This would move the row by 1, which would move down, and then right. So these are the directions that a rook can move, up, left, down, or right. They're orthogonal directions. Now, here's an interesting line of code that I think is really useful to know in Python how to do something like this. It's just a succinct way of writing an if statement that has 2 possible conditionals. It's similar to question mark notation in Java, if you're familiar with that. But basically, instead of what we could write is we could say if self.white to move enemy color equals black, else enemy color equals white. So this is probably the if notation that you're more used to. If self.white to move, set a variable equal to something, else set the variable to some other value. But what I wanted to do here is I just want to do this in one line of code. And essentially, this is what this line does. So what this line of code does is it says, let's set a variable enemy color equal to black if it's whites to move. If this condition is true, this will happen. Else, let's set it to white. So this one line takes the place of these 4 lines of code here. All right, so I'm gonna erase that, but just if you need to go back through that in the video, feel free to refresh that concept. But this is just a nice succinct way of doing it all. All right, what next? So now what I do is I go through the directions for D and directions. So D is going to be equal to this pair here, and then this, and then this, and then that. And I'm going through now potentially 7 values for I equals 1 to 7. Range 1 to 8, but recall that that's going to be that's going to give me the values 1 to 7. And so what I'm going to do is I'm going to take the end row where my rook could potentially move and set it equal to its starting position plus whatever direction it's moving in times I, where I is 1, then 2, then 3, then 4, then 5, then 6, then 7. And so I'm potentially moving up to 7 rows. And same thing with column. And so this becomes really important that I have the zeros here, because when I multiply it by 0, it will not change the column, it will only change the row. And then this next pair doesn't change the row, only changes the column. You can see how that will work. And then all I have to do is I just have to make sure that it's still on the board. So I'm going to check for the end row, make sure it's between 0 and 8, 0 and 7, 0 less than equal to end row less than 8. Same thing for the column. Make sure that square is on the board. And then finally, I'm going to check this, grab the value of the end piece here, and check to make sure that it's an empty square. So a rook can move until it runs into a piece. So if the square is empty, then we should append that move. And that's what we do here, same as our pawn moves. If that square is not empty, then we have to check to see what type of piece is on there, or really what color of piece is on there. And so here, if end piece is the enemy color, and remember I set the enemy color up here. So if the end piece's color is the enemy color, then that's a valid move. I can move to that. But I cannot jump that enemy piece. And so at this point, I break my for loop. That breaks this inner for loop and causes me now to check another direction. All right. And if it's a friendly piece, so that's the other condition. So it's either empty, it's an enemy piece, or it's a friendly piece. And if it's a friendly piece, then I can't capture a friendly piece, obviously. So then I just break. And then it then goes to the next direction. And as soon as it gets off the board, it also breaks. So these are the 3 breaking conditions. I either get to a square that's off the board, I get to a friendly piece, or I get to an enemy piece, and then I stop checking that direction. All right, so that's the rook moves, and hopefully those are pretty clear. And now hopefully you can see how I could apply this logic to the other moves. Let's actually go to bishop moves, because I think bishop moves are more similar to rook moves, but in diagonal. So I'm going to scroll down to the bishop moves, and you're going to see very, very similar pattern to this. I have directions, but now the difference is I'm changing the directions. Which way can bishops move? They can move diagonally, not orthogonally. And so now I have to change the row and the column by the same amount. That's how I stay on a diagonal. So I either change them both by -1, -1, or I change them both by 1, 1, or I change them by 1, -1, or by 1, 1. So I'm looking in toward the top left, toward the top right, toward the bottom left, and then toward the bottom right. The 4 diagonals. These are the 4 directions. Grab the enemy color, same way I did in the other function, and then I go through same idea. A bishop can potentially move 7 squares, right? And when a bishop is on the diagonal here, it can move 1, 2, 3, 4, 5, 6, 7. So that's the maximum amount it's ever going to be able to move in one direction. So that's where this came from. So bishop can move max of 7 squares. All right, now I again end row and end column, and I check to make sure it's still on the board. And then if it is on the board, I grab the piece to see if it's an empty square or if it's enemy color. So this is actually the same thing as the rook. You'll notice that these two are very, very similar. In fact, pretty much all of this is identical. Really the only difference is I'm changing the directions here, and that's the only difference between bishop and rook moves. It's what diagonal you're going to. Otherwise, the pieces move in the same way. It's just which direction you're moving. So that method should make sense as well. Now let's go to the knight moves. And the knight moves you can actually do in a very similar way again. Now, knights can move in 8 potential squares. They move in L's. So here I've listed out the coordinates of where they can move. -2, -1, -2, 1, -1, -2, and so on. Any combination of +or -2, +or -1. So there's 8 total. This time, I'm actually going to grab the ally color. I could have grabbed the enemy color again. Here I grab the ally color. I guess I could have said enemy color, and if it's enemy color, I don't know why I did it this way, just the way the logic worked, I guess, in my head when I was writing this. But what I do here is I say for each of the moves in the knight moves, I didn't name it direction this time. It's not really a direction. It's more of a move. For each of the moves in the knight moves, add the end row and end column. Notice I don't have to iterate through here. I don't have to do times I anymore like I did in the bishop moves. moves because we're just adding these values here. So we're going through the list. Again, check to see if it's on the board. Then grab the piece. A knight can hop pieces, so I don't need to worry about running into an enemy piece or an allied piece. All I need to worry about is my landing square. If my landing square is empty or has an enemy piece on it, then that's a valid move. And so here I just check to see, does my end piece, as long as it's not an ally, that means it's either empty or an enemy piece, then I can append that move. So that's my knight moves. So now we've got bishop moves done, we've got rook moves done, we've got knight moves done. And I hope for the queen moves you came up with this very clever solution for it. Think about a queen, it's just a rook and a bishop. That's all it is. It's just a rook and a bishop combined. So a queen can move like a rook can move and like a bishop can move. So you don't need to write any code for this function. You can just call these other two functions. And I think that's a very, very nice way of doing this. This is a great example of an abstraction right here. All right, and then finally, king moves. Did this very, very similar to my knight moves. These are the possible 8 landing squares. A king can move in any square around him. So again, as long as it's not covered by an ally piece, go through the list. So here I just go through the list of pieces here for I in range 8 moves here. So from 0 to 7, these are my 8 king moves, just adding the 0 and the 1 to it. I did this one a little bit differently here. It looks a little bit differently than my knight moves. I used a for each notation here for the knight moves, but for the king moves, I used the I notation. And I did this because of a thing that we're going to do later in Czech for a more advanced version of this. So if you're wondering why I switched up, that's why I had to actually modify that. But same idea. Make sure the king lands on the board and make sure it's landing not on an ally piece. And if those two conditions are true, then the king. So the king should have been very similar to the knight, and the queen should be just basically the rooks and the bishops. And then the rooks and the bishops are very, very similar, just what direction you're moving in. So I'm gonna stop this video here. So this is gonna be just a video focusing on moves. And I'm going to post another video next on going through how to actually check for checks. So as of right now, what we have is, we can now play the game. It will only allow us to make valid moves, generally speaking. The only problem is right now, the king is clearly in check from the queen, and it will let me do a move like this, which is not allowed in chess. Obviously, you cannot let your king get captured like that. And so that's kind of the next focus on this. I do actually want to add one more quality of life thing. So one of the things you're probably realizing is that if you click a square, let's say I click a piece, and then I click another piece, and I want to move that piece, you'll notice that the clicks get off, and I have to you see it thought I clicked C3 first and then C2, so it thought I wanted to move a piece from here to here. And so if I say click this pawn, and then I decide actually I want to move this pawn and move it here, it registered that as my second click, and so it cleared the clicks. And so then I'd have to basically waste a click, and then make it move. And you're probably running into this as you were testing. So I'm gonna put in a quick fix for that. So let's go over to our main here, and where do we handle this? It's actually right in here. So when we make a move, actually after every second click, we reset the player clicks here. And I'm gonna suggest that we actually do this a slightly different way. So what I'm gonna suggest we do is instead of we should only reset it if the move was a valid move. So I'm going to tab these two lines of code in here. And then we're going to add an else in here. So if it was an invalid move, potentially the user just did a second click on another piece, and we want to save that click. So all we're going to do is we're going to save So the square selected will actually still be saved because we won't clear that. So the square selected will still be equal to that new row column. And so we're just going to set players clicks equals to the current square selected. So instead of resetting the clicks, I'm basically going to set the current clicks to the current square selected. And just that really simple fix of indenting these two lines and then adding this else conditional allows us now to fix this error that we were having before where, okay, I want to move this piece. Oh, wait, I want to move this piece. So that's my second click. But now you'll see, okay, so it tried to do that move, but that move didn't work. And then if I click here, you can see that I only did 3 clicks. I did E2, D2, D4. So I clicked here, here, and then there, and it registered that as a move. Whereas before, I would have had to click here, and then click here, and then I would have had to waste a click. So I would have had to click on this again, and then click, and then it would work. But now you will see a little bit of an error there, which it didn't work there when I clicked on it twice, and that's because I deselected it. So now our select deselect function works. So if I click the same piece twice, it's actually deselected. So if I click this piece twice, I obviously can't move it. Deselected. If I click this once, then I click this once, then I move it, it will move. Click this, it'll move. So now it should be a little bit more intuitive of a feel to it. So that's just a little quality of life thing that we're going to add in. All right, so like I said in the next video, I'm going to look at checks and checkmates, and we'll move from there. All right, thanks for watching. I hope you're enjoying this series.